So let me bring up the PowerPoint first.
Yeah, I see some friends from Tsinghua and the Zhejiang University online. That's good.
Oh, okay.
So you know Professor Liu Feng?
Yes, of course.
Yeah, we are friends. Yeah, we are friends.
Hi, Stephen.
Hi, how are you?
Fine.
Okay.
How are you? It has been 5 or 6 years since I left.
It's a long time.
Yeah, very, very
刘
long
峰老
time.
师，老师你好。
冯生，my
we cannot
video
see you.
seems my
Yeah,
video
we
seems
cannot
some
see you.
problem. I
Okay.
just need to use.
So am I sharing I'm sharing my screen, right? Or
we cannot see it. We cannot see it. No.
刘老师 make Steven co-host。
我的 video 好像有点问题，我找一个外接的。
换一个电脑吧，看那个小白点。
Is there another?
But it says on my laptop that I'm sharing screen, but I don't see it on my iPad either. So strange. Let me try again. Pause sharing, stop sharing. Okay. Share screen. Share screen. That's very strange. It says on my laptop that I'm sharing screen, but I don't see on my laptop iPad either. So
we don't listen.
yeah. Let's see. Why is that? Let's see. Stop sharing.
Which one is your laptop account?
Oh, I may have, so maybe I'm joining the wrong session on the laptop. So let me try again.
Yeah, I didn't see it.
So am I joining the right thing?
Yeah, I saw another Steven.
You see my second one? Or?
Yep.
Oh, okay, great. So if I share screen, yeah, share screen. Okay, sorry.
Okay, that's good.
So do I? Oh, maybe the spotlight. Oh, maybe I can do it.
Verena is all white.
It's not all white. Maybe it takes. Yeah, it looks all white to me too. Maybe it just takes time to come up. I don't know.
So this is PowerPoint or PDF?
It is PowerPoint. It's a large file though. So
okay.
I don't know whether that makes a difference. It's just screen sharing, so I don't know why it takes so long. Sometimes there's connection issues between Australia and China.
Yeah. No worry.
Let's see. It has still not come up, right? But it says the screen sharing, it's paused. What does that mean?
But we are viewing your screen right now.
Yes, but on my laptop, there's a little message that says your screen sharing is paused.
We are not. Are we sharing?
Oh, we can sort anything.
Now this is my whiteboard. Okay, what about?
You're sharing your whiteboard.
So somehow it's only see the whiteboard. It doesn't see my PowerPoint. Okay, so let me start sharing again. Let me just share the particular to select pose. Okay, how about this?
Oh, that's good. Camera.
Ah.
Great.
All right, finally.
Oh, it's very on time.
Okay.
Okay, perfect. Okay,
So shall we start?
Yeah, shall we start? And good morning, friends, and good morning, Professor Low. Thank you very much for coming to the engineering seminar in Peking University. I know you have been visiting many universities in China, but hopefully you will come to visit us in near future, because you now have 2 students in Peking University, like Peng Chen and also Yu Jie will join us in the summer. We are very happy to have them to our department, to our college, and also to the Peking University. Okay, so I'm Jie from Department of Industrial Engineering and Management. And okay, so today we are very looking forward to your talk about learning and control in distribution network. I think we have many PhD students, and also we have some your friends from the world coming to the talk. And now, Peng Chen, it's your time to give a more detailed introduction to Professor Low. And also, thank you very much, every friends online. Okay.
Thank you,
Yeah,
Professor.
thanks, Professor. So good morning, everyone. My name is Peng Chen You. I'm assistant professor in the same department. And also I want to thank Dr. Jie Liu for organizing this seminar. So we are very happy and honored to have Professor Stephen Low from Caltech today as our guest speaker. He will be introducing the research on smart grid optimization in Caltech. Let me briefly introduce Stephen. So Stephen is the Gilmour Professor of the Department of Computing and Mathematical Sciences, and also the Department of Electrical Engineering at Caltech, and also honorary professor of the University of Melbourne, Australia. So he is a recipient of many prestigious awards, including the IEEE Infocom Achievement Award, the ACM Sigmatrix Test of Time Award. He is a fellow of the IEEE ACM and the CSEE. He received his Bachelor of Science from Cornell and PhD from Berkeley, both in EE. I also want to mention that Stephen has 2 startups,
Wow.
FastSoft and PowerFlex, that respectively commercialize his research on fast TCP protocols and electric vehicle charging. So, okay, let's welcome Stephen. It's all yours.
Okay, thank you very much, Professor Song and Jie Liu, Dr. Liu, for arranging this, and also thank you very much, Peng Chen, for the introduction. It's great. I've only visited Peking University, Beida, once physically, but of course I heard of the 2 universities, Beida and Tsinghua, a lot since my high school, before my high school actually. Lots of legends from both universities, so it's fantastic. So it's great to be able to, it's an honor to be able to present here, and also great to see Yu Jie online.
Yeah, we see Yu Jie there.
Yeah, and also Professor Feng Liu from Tsinghua University is fantastic, and John from Singapore. That's great. Okay, so I'll talk about learning and control in distribution networks, and let me. Okay, it doesn't advance. Okay, so I'm not sure what the background of the audience is, so let me spend a couple minutes on just the motivation. So some of you already know all of this. The reason we're very interested in energy, but also in power system in particular, is that, let's say in the US, for example, the greenhouse gases, the 84% of the greenhouse gases are due to energy use. Of this 84%, 2 activities, electricity generation and transportation, they consume about 2/3 of all primary energies in the US, probably similar in China. So the primary energies are, say, the coal, the gas, the petrol, the nuclear, hydro, renewables, all of those primary energies. About 2/3 is used for electricity generation and transportation. And the two activities emit about 55%. So between 55% and 60% of all greenhouse gases. And therefore, if we want to drastically reduce greenhouse gases, we have to electrify transportation and we have to generate electricity from clean renewable sources. So that's the reason, these two. And indeed, the renewable or clean energy is happening, has been happening, and China has been playing an extremely important role globally in the development of renewable energy. So this is just one example where the photovoltaic price has been dropping exponentially. So in 1976, it's $79 per watt, and 2016 is 37 cents. And again, China has been really. If you look at the batteries, lithium-ion batteries, and the batteries for different applications for electronics, for electric vehicles, but also for grid-scale applications. If you just look at the electric vehicle applications, that also has been decreasing quite substantially over the last, say, 1 or 2 decades. So in 2010, it's about $1,000 per kilowatt hour. By 2016, it's under 300. If we look at the wind capacity that is installed in the US, so the wind capacity has exceeded the hydro capacity, which is a very mature technology, has been deployed over decades. But wind capacity has exceeded the hydro capacity by 2016. And the wind generation has been higher than the hydro generations in the US. And here's another interesting data from international energy agencies. In their World Energy Outlook, they predict PV adoption every year. So there are many curves, one for each year's prediction. And the interesting thing is that the actual trajectory, the actual adoption rate has far exceeded the prediction consistently. So these are all good news. By say 2018 or so, wind and solar has already become the cheapest. The levelized cost is already the minimum among all generation mixes. So even cheaper than the gas, the natural gas. And therefore, the good news is that the renewable generation will indeed replace thermal generation because the economics has flipped. The challenge, of course, is that it introduces the challenges that must be overcome, right? Because the grid was not designed for large scale, say, uncertain and undispatchable generations. So, and there are many interesting issues, important issues. And one of some of them happens in the distribution network. So distribution network is probably many of the smart grid innovations will first appear. And the distribution network in particular will contain endpoints that are not just passive loads as in the past, but some of the endpoints may generate, so this may be PVs, maybe wind turbines and so on, but also some may communicate, compute, and actuate. So this could be, say, smart EV charging, smart buildings, smart appliances, smart power electronics, and so on. And therefore, you have a very active system in distribution networks. And that introduces both risk and also opportunity. It is a risk because now you have a lot more uncertainty in the supply, in the demand, in the power quality in the network, and therefore the potential for cascading failure is increased. On the other hand, these are also distributed energy resources that are intelligent, that are networked. And therefore, if we can close the loop and control them at scale, we could improve the security, the robustness, and the efficiency of the entire system. So that's the opportunity. So what I would try to do is to maybe quickly summarize 3 pieces of work. The first piece is about learning the topology and line parameters of a distribution system. So it's work by Yue Yan, who is a professor at Huazhong University now, who was a postdoc several years back at Caltech. Amir Adakarian at University of Alberta, and also Tom Conlon at Berkeley. The second piece of work is mainly the work of Huan Nanqu, who is now a professor at CMU, the WE department. He was a postdoc at Caltech about learning-based voltage control. That is, if you don't know, so the first part is about how do we learn the network topology and line parameters. And the second part is about if we don't know that, or also if we don't know the nonlinearity of the power flow in the network, for example, can we still do voltage control based on the measurements? And the third piece is a very different kind of work. Our work on large-scale smart EV charging that Peng Cheng mentioned at the beginning. So these three separate pieces of work. So the first piece is about learning admittance matrix. So admittance matrix will tell you both the topology and also the line parameters. And so I will formulate the problem and then just tell you the major result. And the major result was surprising to me. It says that if you have a network with tree topology, what's called radio network, assuming single phase. So that's a little bit different from the reality of distribution network. But if you have a tree topology network, and if you have measurements only at some of the nodes, but not all of the nodes, it turns out you can still exactly recover the topology and the line parameters. Okay, so the first part, the problem formulation. So a network, you can think of it as a graph with the set of nodes and n bar, and also the lines. And every line is parameterized by a single complex number yjk, which represents a series admittance. So for those of you who are familiar with what's called the pi equivalent circuit model or transmission line, that is the series admittance. And in particular, we assume the shunt admittances to be zero, which is a reasonable assumption for distribution system. And this is characterized by a single complex number yjk, which is a series admittance. So that's the model. It's very simple. And if you look at the current injection from each node j to the rest of the network, it depends linearly on the voltages in the network. So every quantity is a complex number. So ijk is a complex number that represents the current injection phasor. And voltages, Vj, is the voltage phasor at node j. It's just some complex number. And the relationship between the vector of all current injections and the voltages in the network V is linear, described by this admittance matrix Y. So Y, this matrix, can be represented in terms of the line parameters. So given a topology, given the line parameters yjks, you can write down the matrix Y, which is this admittance matrix. And our goal is to identify this matrix from measurements of I and V. Okay, so that's cool. So the important thing to know is that Y, we assume, is that because it's complex symmetric matrix with zero sum. And zero sum comes from the assumption that the shunt admittances are zero. So if this shunt admittances are zero, then you get this property, these two properties of the Y admittance matrix. Notice that the matrix is complex symmetric, but not Hermitian. And that's where a lot of computational issues comes in, that it is not a Hermitian matrix, but it's complex symmetric. So the learning the admittance matrix Y, for example, is the following problem. Suppose we have measurements of the current injection at every node I and the voltage phasor at every node I at different times t equals 1 to capital T. So at each time t, you have this linear relationship between the current vector I of t and the voltage vector V of t. Right? It's given by this simple expression in terms of the admittance matrix Y. If you have measurements at multiple times, then you can write down, let's say, for each node I, then there's a vector I, the current at node I, but across time t, right? The superscript capital T means the measurement at node I, but across time t, in terms of the voltages at all nodes at all times. So you can write the voltages in this matrix form, then you get this expression in the in row of the admittance matrix Yi, right? So you just get a linear relationship that will allow you to solve for this Yi if the matrix V capital T is say full rank, for example, right? So just a simple notation. So the capital T means that it is a matrix of measurements across at all times, and then V of a different form of T, that's the transpose. We don't use that much. Okay, so therefore you can formulate the problem learning about Y as you want to choose a Y matrix that minimizes the forbiddance norm from your measurement, subject to the two properties that Y is complex symmetric and Y has zero sum. Right. So among the set of Y's that have these two properties, you want to choose one that will minimize your error, basically. Now, in particular, if this matrix V of T, the voltage measurement at all times, at all points, this matrix has full column rank, then you can identify an exact solution. And by exact solution, it simply means the error is zero. It may or may not be ground truth. If there's no noise, then you will be ground truth. And then it simply means that if your voltage measurements are sufficiently rich, then you can recover the ground truth Y exactly. Okay? Otherwise, this Y will just give you the minimum error. Now, then you can formulate different problems based on this basic idea that, for example, you can assume different statistical properties of your noise, and then you can do different things, how you choose a optimal Y and so on. So we want to focus on different problems. So this formulation assumes you have measurement at all nodes. What if you don't? So that's the problem we want to look at. So the setup is that we have a radio network, which simply means a network with tree topology. We assume it's connected, we assume it's single phase. So the radio network assumption is very realistic for distribution systems, but not a single phase. So it needs to be extended to multi-phase, but that's the assumption. So we have measurements at a subset of the nodes, some arbitrary subset of the nodes. So these are called measure nodes. And another key assumption is that at each node where we don't have measurement, we call hidden nodes. We assume the injection is zero. So the rationale is that if there is an injection, typically it means you either generate or you consume. And typically in that case, you will have a meter that will measure how much you generate or how much you consume. In the intermediate points inside the network, you may not measure, but there's probably no injections, no generation nor load. So that's an important assumption, which seems reasonable. And then there's an assumption that it's not that important, that every hidden node has degree at least 3. So these are the assumptions. Under this assumption, it turns out you can recover the original matrix Y from partial measurement. So precisely so, and therefore each time, we're going to use the notation I1 here means the subvector of current measurements at all the measure nodes. And the hidden nodes will have zero injection. So that's this. And V1 are the voltages at the measure nodes. So V1 is a subvector, and V2 is a subvector of the voltages at the hidden nodes, which we do not measure. And we don't even know how many hidden nodes there are initially. Okay? So we don't know the topology, we don't know how many hidden nodes there are, but structurally it looks like this. And you can partition the Y matrix accordingly, Y11, Y12, and Y22. And Y21 is simply symmetric version of the Y12. Okay, and therefore this is the relationship of the current and voltages in the network at each time. If you look at the Cron-reduced emittance matrix, which is simply the Schur complement of Y22 of this Y matrix, right? So this is the Schur complement. So this matrix is also complex symmetric with zero row sum. And therefore it corresponds to some network, and indeed it corresponds to this network. So for example, in the original network, you have the one hidden node 7. In the Cron-reduced network, you don't see 7, but you see connectivity between node 4, 5, and 6. So the Cron-reduced emittance matrix is the emittance matrix for this equivalent sort of Cron-reduced network. Okay? That's what it is. And in fact, it is the matrix, Y bar is a Cron-reduced emittance matrix. It is the matrix that relates the measurements, the measured currents and voltages. Okay? So that's what this Y bar is. And therefore, you can pose the same question, but the smaller scale for the chrome-reduced network, where you want to choose a chrome-reduced emissions matrix to minimize your measurement error, subject to the constraint that the chrome-reduced network emissions matrix is symmetric and zero sum. And therefore, if this matrix voltage measurement matrix V1T has 4-column rank, then we can identify Y bar exactly. Let's assume there's no noise, so that we know exactly what Y bar is. Okay? Now, one thing just note is that because Y is complex symmetric, not real symmetric, it's not obvious this Y bar always exists, but it does exist if the lines are resistively inductive, which are reasonable, which means that for practical network, indeed, Y bar exists. I guess it's no surprise for power engineers. And the question that we really want to focus on is the following. Suppose we can exactly recover Y bar. Okay? So from the measurement, from the partial measurement at the measure nodes, we do that minimization, and then we can get a exact solution Y bar. The question is that can you recover the original ground truth, the Y matrix, from this chrome-reduced matrix Y bar? And the answer is, surprising to me, is yes. So you can exactly recover both the topology and the impedances of the original network from a chrome-reduced Y matrix, and proof is by construction. So in particular, for example, it says that if you have a network that looks like this, where the green nodes are the measure nodes where you have both voltage and current measurements, the brown nodes are nodes where you don't have any measurement. You don't even know the topology, how many hidden nodes there are. But it turns out, if you can recover the chrome-reduced matrix, then you can recover the topology and the line admittances of this original network. Now, in a typical, say, distribution system, then this node is also measured. This is like probably the substation. You can also have measurements, but it doesn't matter. You can have sort of arbitrary set of subset of nodes where you have measurements. As long as they satisfy the constraints, the assumptions, then you can recover the ground truth. So let me maybe in 10 minutes tell you a little bit the basic ideas behind the proof. So this is, again, just remind yourself what the assumptions are. It's a radio network, it's connected single phase. The shunt admittances are zero. The important assumption is that there's no injection at hidden nodes. There's this degree assumption, which is not that important, and that we can exactly recover Y bar. All right. So the three ideas in the proof. One is that we assume we can recover Y bar exactly, and you can indeed look at the underlying graph for that chrome-reduced matrix, and you can decompose them in a certain way, in some nice way, it turns out. And that decomposition allows us to recognize which we can partition the measure nodes into internal nodes and boundary nodes. The internal measure nodes are those nodes that are connected to only other measure nodes, whereas the boundary nodes, measure nodes, are those nodes that are connected also to hidden nodes. So once you have that partition, then it allows us to do a recursion, which basically, starting from the set measure nodes, you can recover a set of lines that connect the measure nodes with the hidden nodes. So, and then you can shrink the set of hidden nodes, and then you can do the recursion, and then eventually shrink the unknown hidden nodes to zero, basically. Then you recover everything. So that's the structure. So let me say a little bit about that. Okay, so we know Y bar, and we know the underlying graph G bar underlying the Y bar, right? So you can write Y bar, decompose Y bar in terms of two matrices, submatrices, Y1 bar and Y2 bar. And they are defined in terms of the submatrices of the original Y. And therefore, we don't know the original Y, we don't know their submatrices Y11, Y12, and Y22. Therefore, we don't know Y1 bar and Y2 bar. But we know if we knew those submatrices, then we can decompose Y in terms of Y1 bar and Y2 bar. So Y1, you can show that Y1 bar, Y2 bar are complex symmetric matrices with zero sum, and therefore they are admittance matrices of some graph. Now, so let's just denote G1 bar, G2 bar to be the underlying graph, right? And G bar is the underlying graph of the Y bar. So what do we know and what do we don't know? Well, we know Y bar, and therefore we know G bar. So this we know. We don't know Y, and therefore we don't know is some matrices, Y11, Y22, and Y12, and therefore we don't know Y1 bar, Y2 bar. Okay. But it turns out we can construct the underlying graph of Y1 bar, Y2 bar from this graph of the Cohen-reduced admittance matrix or Cohen-reduced network. Okay? So it turns out we can do that. And so you can show this property, but let me just describe these properties using this graph. So this is the Cohen-reduced graph, which we assume we can recover exactly from the partial measurement. It turns out, even though we don't know Y1 bar, Y2 bar, if you look at the underlying graph of G1 bar, G2 bar, it looks like this. It consists of G1, which is a disjoint collection of trees, and G2, which is a disjoint collection of cliques with at least 3 nodes, plus some isolated nodes. And therefore, from this diagram, it looks very clear how it decomposes. It decomposes into this thing. In particular, G1, G bar have disjoint edge sets. And this structure allows us to actually construct Y1 bar, Y2 bar from just the Y bar. And therefore, just to recap, so from the partial measurement, we can assume we can recover the exact Y bar. From Y bar, we can construct the underlying graph. From that underlying graph, we can decompose the underlying graph into these two very special G1 bar, G2 bar that tells us the topology of the G1 bar, G2 bar. And from there, we can figure out the line parameters and therefore the Y1 bar, Y2 bar. So now we know Y1 bar, Y2 bar. We don't know the submatrices of the Y matrix, but we know Y1 bar and Y2 bar. And this will be used to compute the parameters later on. So that's step one. Step two, from that, we can recognize, so all we see are the measure nodes. We don't know anything about the hidden nodes. But now we know that these nodes, this set of measure nodes are what's called the internal measure nodes that are connected only to other measure nodes. But this set of measure nodes are connected to some hidden nodes. So we can partition them. And therefore, the Y matrix, which we do not know, can be put into this form. Is some form. Let me skip the details. And then also, we're going to call this boundary hidden nodes and internal hidden nodes that are connected only to other hidden nodes. Okay, so it has. We know the Y has this structure. And it turns out with this structure, you can actually figure out the internal lines, the parameters on the internal lines between measure nodes. So you can calculate this, and therefore what remains to be calculated will be the other submatrices. So we can just focus on the other submatrices to say, okay, how do we recover that? That corresponds to ignoring from the graph, ignoring those internal nodes, internal measure nodes. Just focus on the set of hidden nodes, which we know nothing about yet, and the boundary measure nodes at which we have measurements. So that's the subgraph that we focus on. That corresponds to this submatrix sort of. Okay, so let's just focus on that and see what can we understand about this subnetwork. Then you can show that what you can do is that you can partition the set of boundary measure nodes into groups so that every measure node in that group is connected to the same hidden nodes. So we don't know where the hidden nodes are, but we know this set of measure nodes are connected to the same hidden node. Okay, and therefore for every hidden node, we know the set of measure nodes that are connected to it, which means that this Y1122 and Y122 on these two submatrices must have this form. So this is basically the set of measure nodes connected to the first boundary hidden node and the second one, and so on and so forth. You must have this simple form. And this simple form allow us to recover these line parameters from Y2 bar, which we figure out from step one. And therefore, that allows us to do the recursion. So let me skip the details of, okay, so one more comment. So from Y2, we figured out this, this structure. These are all about the measure nodes. The hidden nodes are here, but this structure, because of the complex symmetric property of Y, has implications on the structure of the hidden nodes. So let me skip the detail of what that structure is like. The important point is that it allows us to do the recursion. So let me describe the recursion in diagrams. So the recursion is eventually allows us to recover the entire network. So let me describe the recursion in diagram rather than try to explain these matrices. So suppose we have this network. All the green nodes are measure nodes. The solid green nodes are the internal measure nodes. They are connected only to other measure nodes. The empty measure nodes are the boundary ones, which connects to some hidden nodes. Okay? Similarly, on the brown nodes, so those are hidden nodes that are either internal or boundary. Okay? So the way this recursion works is that you first figure out the line parameters, the topology and the line parameters of these solid green lines, which are the internal lines. Okay, so it turns out you can, from Y2, you can figure out what those line parameters are and the topology and line parameters. And then what that allows you to do is to effectively turn the boundary measure nodes, these empty measure nodes, into effectively an internal measure nodes, and turn the boundary hidden nodes into boundary measure nodes. So they will have the property such that it's as if you have the measurement at those boundary hidden nodes. So the next iteration looks like this. So these empty brown nodes that were hidden nodes at the boundary now becomes as if they are measure nodes at the boundary. They are connected to some hidden nodes, and those becomes now the boundary hidden nodes. And therefore you shrink sort of the boundary of your hidden network, right? One step, and you just repeat. Eventually you shrink until the hidden network is empty. That's how you recover the entire Y matrix. So that's the first part. Okay, let me look at the time. Okay, good. So let me talk about the second part, which is, so the first part is about, under the assumptions, let's say tree network but single phase. If you have partial measurements, you can recover the Y matrix. In this case, Guanan's work is look at the voltage control on distribution system. Again, radio network, single phase. So these are the assumptions. Suppose you don't know the topology, and you also, importantly, you don't know the exact nonlinear power flow equations. Can you still do the voltage control? So that's this problem. So the motivation is that you have a distribution system. The voltage at every point in the system, in the network needs to lie within a certain bound of, say, around, say, 5%, within 5% of your nominal value, let's say. Now, because of the load, because of the distributed generations, you may have voltages that may violate its lower bound or its upper bound. And therefore, you want to control, say, the reactive power at, let's say, the power electronics inverters, for example, or capacitor banks, for example, so as to make sure that the voltages in the network will lie between those limits. So that's the problem. So a lot of work on this problem, different assumptions, different control algorithms, and different properties, convergence properties, and so on. All of this work, including our own, assumes that we know the topology and the line parameters. And some of them, including our own, assumes the power flow equations are linear. So under these assumptions, then you can design different algorithms and prove different properties and so on. So what Guanan looks at is, what if we don't know the topology? What if we don't know the line parameters? And what if the power flow equations are nonlinear and unknown? Okay? So can we do that? How do we do that? So how do we deal with the lack of model information and also the nonlinearity, which is unknown? And his method is to use online learning from the measurement, the voltage measurements, as we will see, to deal with the lack of model information. Basically, that's where the learning-based control, the learning part comes in. And to deal with nonlinearity, you try to track the Jacobian, as we'll see in more detail. Basically, that's the approach that he uses to deal with this problem. So here's a formulation. We have a distribution network. We're looking at steady state behavior, and therefore it's described by powerful equations. The control is the reactive power at some subset of the nodes. So think of, let's say you have distributed energy resources like the solar panels or batteries or EVs and whatever it is that's connected to the grid through, say, an inverter, and you can control the output, the reactive power output of the inverter, and that's the QT. So QT is the vector of reactive power at a subset of the nodes. The voltages on the network depends on the control through this nonlinear function V as a function of Q at time t. Okay, so we're going to assume Vt is some nonlinear function that is unknown, but with some vicious conditions. So the behavior of the network is essentially described by this V of Q. So you apply the control Q of T, the network will solve powerful equations, and you can measure the voltages in the network. So the assumption is that you have measurements at all the voltages, voltage measurements at all the nodes. And then your controller will choose a new QT plus 1, and you repeat the cycle. So this closed system. The goal of the controller is such that the feedback system is asymptotically stable. So you will converge to some equilibrium point, such that that equilibrium point is an optimal solution of this optimization problem. So the cause is some function of the control, and what you want is that in equilibrium point, the voltages satisfy its upper and lower bound. Okay, so that's the setup, that's the formulation. Again, you have a closed-loop system where the voltage is a function of the control Q, and you do this iteration, and what you want to you want to design a controller so that this VT QT trajectory converges to equilibrium point, which is the optimal solution of this. And the challenge is that V of Q is nonlinear and also unknown. So that's the challenge. So how do we think about this, right? The way you think about this, what Guanan did was to first assume we know VQ and it is linear. What do we do? And then from that, you try to figure out what you should do in the case of nonlinear and unknown VQ. So if VQ is known and linear like this, right? So this is the linearized disk flow model, some of you may know. Then V is linear in the control Q with the X matrix, which is positive definite, which is known if you know the topology and the line parameters. Then you know XQ, and then some known vectors. And of course, the problem that Guanan looks at is if you have this nonlinear function. And therefore, V is some nonlinear unknown function of Q. And the assumption is that VQ is differentiable and Lipschitz with the constant L. And the Jacobian is also Lipschitz with Lipschitz constant L prime. So that's the assumption of VQ. That's all you know about this function VQ. Okay. So what do we do? So let's look at the case when the power flow model is linear and known, and see what do we do. So here's a proposal by Guanan a few years and Nali and Manza in 2016. So what you do is that you compute QT as a function of the Lagrange multipliers lambda under bar, lambda upper bar. So these are the Lagrange multipliers associated with the voltage limits. Based on the Lagrange multipliers, you multiply this by this control gain. A inverse and X are depends on your network model, linear disk flow model. And in particular, this X is really the Jacobian of the voltage with respect to Q, with respect to the control. And you adjust the Lagrange multiplier in this way. And what this is that we have this optimization problem, right? A few slides ago. You look at the dual problem. You apply gradient algorithm to the dual problem, then you get this dual ascent algorithm. Okay, and therefore this is a dual ascent algorithm to solve the dual problem. And Guanan shows that under those assumptions, indeed, it does the right thing, that the closed system is asymptotically stable, it converges to equilibrium point that solves the primal and the dual problem of the optimization problem. So that's the case in the linear, if we know it's linear and known. What if we don't know and it's non-linear? Well, the idea is that you maintain the same structure, but you try to estimate the Jacobian with some x bar, x hat of t. Now, no matter how you estimate x hat of t, what Guanan shows is that as long as it tracks the Jacobian, so J of t is a true Jacobian dv dq, which we don't know. But if the x hat tracks jt in this sense, you satisfy this error bound, and beta t is some square summable sequence. As long as the error satisfies this bound, then this algorithm will do the right thing, that it will converge, and any limit point, well, you may not converge, any limit point will be optimal and for the primal and the dual problem, right? So that's the first result. So how do you make sure, how do you come up with an estimate x hat that will satisfy the bound? So here's Guanan's design. Let me, because of time, let me skip the details of this design, but let me just tell you the intuition. So the intuition is that at each time t, the way you figure out your x hat, right? So what this computation does, you can interpret this computation as doing the following thing. You look at the weighted sum of all the past error up to time t. So you can think of the error, this delta v and this x hat delta q stuff, as the error that captures two things. One is that you assume the error due to nonlinearity. That's the first thing. The second thing is that there's certain excitation noise that you inject deliberately into your computation. So that excitation noise is such that you get rich enough measurement. And that excitation noise produces a certain error. And therefore, this error really arises from two things. One is due to nonlinearity, one is due to this excitation noise. So each time t, you look at all the past error, weighted exponentially, and then you try to choose the matrix for time t that will best account for all the past error. So that's what that computation is. If you do that, then this x hat t, how you track the Jacobian, indeed will satisfy the error condition that Guanan proved earlier. And therefore, if the step size of how you adjust your Lagrange multipliers is small enough, then it does the right thing, that any limit point of the closed system will indeed be primal and dual optimal. Okay, so let me just close by a simulation. This is Southern California Edison 56 bus distribution circuit. So this is the performance in terms of the cost of the original dual ascent controller, meaning that you assume the network is linear and known, and then you do your dual ascent algorithm. But the network is actually nonlinear. It satisfies the original disk flow solution, for example. Then you are sort of applying the wrong control, basically, and you will converge to a higher cost. Whereas if you use the proposed approach, then indeed it attains optimal cost. In terms of the voltages, indeed you can stabilize the voltages within their limits. Okay, so in summary, indeed you can have learning-based feedback control to deal with unknown and nonlinear model by doing that linear-based control that Guanan designed. Okay, so that's the second part. Let me tell you maybe in 10 plus minutes or so, this third project that we've done at Caltech is the adaptive charging network for electric vehicles. Many people have contributed that to this effort, and Zach Lee, whose PhD thesis is on this adaptive charging network research portal. So that's his PhD thesis. He graduated, is now working at PowerFlex, which is the Caltech startup. It was acquired by Caltech startup. Sunash Sharma, who was an undergraduate at Caltech, who's now pursuing PhD at Berkeley, and Tongsin Lee, who is a PhD student at Caltech and is graduating. Okay, and again, many people have contributed to this effort, and I just want to acknowledge them. In particular, the PowerFlex people and all the engineers and PowerFlex people. George Lee, who is a former student at Caltech and who really started this project by inventing the smart charger using open source chipsets that really got everything started. George Lee. And many people over the years, students, visitors, summer students, and so on and so forth. So just want to thank all of them. Okay. So I will tell you both the physical infrastructure and then the research portal that's actually built on top of that. So the physical infrastructure, the motivation is somewhat obvious. California, for example, has committed to have clean, renewable electricity 50% by 2030. So when it was first formulated, it's 50%, but now it has been changed to 60% because we overachieved. So that's great. And 100% clean electricity by 2045. And have 5 million EVs or zero emission vehicles, mostly electric vehicles, by 2030. So in comparison, California has 15 million cars. So now, according to some statistics, California has about 1.2, I think, million EVs now. It's slightly less than half of all the EVs in the US. For those of you who know this duck curve problem, right? So this is the real duck curves, no longer a prediction. This was a duck curve in 2021. If you want to fill the valley using workplace charging, then this valley can charge 13 million EVs. And therefore, if you do workplace charging, you could potentially combine sort of two challenges. One is the duck curve challenge. The second challenge is that EV is going to need a lot of electricity. So that's going to stress the network. But if you can combine these two problems to be sort of a solution. Another motivation is that there's some surveys that shows people are twice as likely to get an EV when workplace charging is available. So it's good to have workplace charging. So that's the motivation for us. The physical system is that's built by George and team consists of first started at one of the garages. Now there are other garages at Caltech. The first deployment consists of these two three-phase transformers, 150 kVA, and all these panels and breakers and everything, and eventually connects to this smart chargers that George built. That's a physical infrastructure. This is a cyber infrastructure where when a driver plugs in their EV, the traditional, even the current, most of the current product, what they do is that when drivers plug in their EV, you will be charged at the peak rate. So that's the problem that we want to address. If you have 5 EV chargers in the garage, that's fine. If you have 500 EV chargers in the garage, then it's too expensive. You need to build a really large power distribution network to support that kind of large-scale EV charging. And it's unnecessary if you do the scheduling. Right? So that's what we do. So when the driver plugs in the EV, it uses the mobile app to tell the system 2 pieces of information. How much energy do I need? Say, I need 30 miles or 30 kilometers. Secondly, I plan to leave at 5 p.m. today, for example. With this information, so it's sent to the cloud and everything, with this information, then the system will form a convex optimization problem, the QCQP. This is the original linear program, but now the system solves a QCQP every 2 minutes to obtain the charging rate for every EV in the garage for the next 2 minutes. Then after that, you form a new QCQP and then solve again, the cycle repeats. And therefore, it's a standard model predictive control. It's very flexible in that the objective function can calculate different things. depending on the site host. So the site host can say, I want to charge in a way that I will satisfy the energy demand of all the drivers before their deadline, but in a way that minimizes my electricity bill, for example, which may consist of an energy cost, but also a demand charge that's based on the peak rate of your garage, for example. Or I want to charge as fast as possible. Or I want to maximally utilize my on-site PV generation, for example. So all of those properties, depending on the site host, can be incorporated in the objective function. And then there are constraints, which are not shown here. This is just an example, can capture the energy constraints, the deadlines, the capacities, capacity limits of your, say, transformers or breakers and so on. And also, say, priorities. And there are many things you can capture by different constraints that would determine the charging rate for all EVs. Right. So the important things are you want to satisfy the energy demand for all the drivers before their deadline, whenever possible. You want to do it in a way that is safe. So that's the first garage that that was energized on early 2016. That's George and his brother working late at night, the night before this garage was energized. So this was the first generation charger that George built. Now it's all replaced by commercial off-the-shelf hardware with his chipset. And these are transformers and so on. This is operational since 2016. By July 2020, it has delivered 1 gigawatt in this garage, corresponding to 3 million miles, 5 million kilometers about. And then we deploy them at other places, JPLs, and so on and so forth. So the startup was acquired by EDF Renewables, one of the largest utility companies based in France. So this, I'm just going to show you some pictures. So this shows this 2018. This is time on the x-axis. This is the charging rate in amps. Each color curve corresponds to the charging profile of one EV. So there are tens of curves, which shows you can fluctuate depending on the optimization problem, the solution of the QCQP. So this shows, this is installed at NREL. This shows you can, in fact, control based on real-time information. For example, in this case, you want to control it so that the net demand from the building has a peak rate that does not exist, in this case, 40 kilowatt, right? So that controls the demand charge for that business. So this is the building minus PV. So this is the net demand from the building during weekend. So there's not a lot of load. You see this duck curve. During the work days, you still see this duck curve, but there's more low and more fluctuation. But despite the fluctuation, you could control the EV charging so that the total net demand is under 40 kilowatt. The impact of COVID, after mid-March, you get this thing. So that's the physical infrastructure. So before November 2018, it's basically a test bed. We allow people to charge for free, and we encourage people to charge. And it's a test bed. We do whatever, and then things break, and all, people are understanding. After November 2018, it transitioned to commercial operation. So we can no longer just do anything we want and break the system. And therefore, the idea is to build a software layer on top of the physical layer to provide some research facility for researchers. And you have three components. One is ACN data. So we will capture in real time all the charging data, clean them, anonymize them, and put them on the web so that anyone can use them. So these are not only the session data on, let's say, the amount of energy and also the duration for that charging session, but it includes very fine-grained charging rate profile every 10 seconds for every EV, for example. ACN Sim, which implements a very realistic simulator platform, so that if you design a new EV charging algorithm or new pricing algorithm, and you want to evaluate your algorithm using realistic simulations, then you don't need to implement all the basic infrastructure. You can interface with ACN Sim and just evaluate your algorithm So I'll go into a bit more detail later on. And then ACM Live, which is not complete, but the idea is that, let's say you have an EV charging algorithm. Once you analyze it, you simulate it, everything is safe. You can actually, the idea is that will allow you to actually use your algorithm to charge the real cars at Caltech. Okay, so that's the idea. We have the design, but not the complete implementation. Okay, so let me go into a bit detail for each of them. So ACM data, by October 2020, there are 53,000 EV charging sessions with fine-grained data. Everything is open source, open on ev.caltech.edu, is growing daily. You can use this fine-grained data, for example, to model user behavior. So you may be economists interested in how economic behavior, or maybe you have some pricing algorithm that you want to evaluate. You can use that to evaluate the performance of charging algorithms, to evaluate the, say, flexibility of the charging facilities. You can evaluate when you have a grid on which there are many such smart EV charging garages. What is the impact on the grid? Can you use this flexibility to help stabilize the voltage on your grid, for example? Right? So all those things you can use the data to evaluate. Or if you're interested in just machine learning, then maybe you can use this sustainability or EV charging data for some learning problem. So these are just some example of, you can use that to evaluate user flexibilities, say Caltech data and JPL data for a particular definition of how flexible the loads are. You can use it to evaluate the flexibility of this site, the say ACN at Caltech at JPL. So in particular, for example, the JPL and Caltech data shows that at Caltech, if you do uncontrolled charging, you need 3.8 times more infrastructure to support the EV charging demand at Caltech. And at JPL, you need 3.4 times. And therefore, just by doing simple software, you can reduce the capital investment, but also the demand charge. So this is some user behavior. So this is once you transition to a paid system, the number of charging sessions decreases. This is the COVID impact. So you can see how people behave in response to different events. So if you look at for example, the arrival time distributions, it has a larger variance, probably a reflection of some more flexible hours post-COVID. So this is some interesting learning problems. So we have these fine-grained battery charging profiles, say 35,000 of them, for example. But they're really generated by a small number, relatively small number of drivers driving a small number of EVs that probably use a small number of batteries. And therefore, you should be able to just classify these charging curves into only a few types, for example. Well, it turns out it's not that trivial to do that, because we don't know the state of charge. All we know will be the charging current profile. And you need to sort of look at the tail behavior of that in order to classify. Now, how do you extract the tail? That depends on how you classify. And therefore, it makes an interesting learning problem where extracting the tail depends on how you cluster, and how you cluster depends on how you extract the tail. And so you need to do this feedback loop stuff in your learning. So it's an interesting learning problem. And people have used data for different purposes as well. So that's ACN data, ACN sim. So as I mentioned, what Zach Sunas implemented is a very realistic simulation platform that simulates the behavior of the batteries, the EVs, the chargers, the network, the constraints, and so on and so forth. And each piece you can improve. Let's say you have a better battery model, you can implement the model and plug this in, and the basic platform becomes better. It's also integrated with ACN data, so that you can use the real ACN data to drive your simulation. You can also integrate external signals, such as utility tariffs. Let's say you want to evaluate some pricing algorithm. So John and Zach work on this pricing of EV with demand charge, for example. You can use the utility tariffs as part of your simulation, driving the simulation, as well as the real ACN data, for example. Or you want to maximally utilize your on-site solar generation. then you can use the solar generation data and drive your simulations. So it has an interface. As long as your algorithm, whether it's charging algorithm or charging algorithm with some kind of pricing, so on, as long as you can interface with the system, then you can easily evaluate the performance, the behavior of your different algorithms without having to implement this basic infrastructure. So hopefully it's very useful. ACM Live, the idea is that you maintain the same interface. And therefore, once your algorithm, you're satisfied with the algorithm, you're safe and everything, you don't need to change, you can apply your algorithm in theory to charge real cars in the garage, their garage. So the idea is that the system, ACM Live, to capture your command, the charging rate command, check if it is safe. If it is not safe, it's going to use the charging command from the PowerFlex system for the next, say, 2 minutes. If it is safe, you would apply your charging command to the cars, to the smart chargers, charge the car, measure the state, and then pass the state back to your algorithm, and your algorithm can compute the next set of commands. So that's the idea. Everything, all the 3 components, everything is open source, extensible. Hopefully it will be useful for some of you, and hopefully you'll be interested in contributing to this effort or taking over. Zach has graduated, so if anyone wants to take this and take a lead on this, that'll be fantastic. Please let me know or let Zach know. So thank you very much. That's I will stop here. And Zach Lee, he still is supporting this infrastructure, and you can reach him through that email. Yep, thank you very much.
Thank you, Stephen. Perfect time. I think we have half an hour to discuss, and the audience is like welcome to unmute yourself to ask questions.
So let me stop the sharing.
Hi, Stephen. This is Guanan He. Actually, the other Guanan in this talk. Actually, we were very good friends. You know, I visited him at Boston, and we were undergraduate classmates. So I'm currently an assistant professor at the Department of Industrial Engineering and Management at Peking. I work on the optimization of batteries and hydrogen-related technologies. So you have talked about, and also heard that you have made great progress in the commercialization of your work with regard to EV charging, which is what we showed. And that's a very amazing achievement. And so my first question is, so you might also have heard has been very hot, or
worked on that. The content expert on that.
Yeah. Yes. So what do you think? Do you think it's a competitor for the battery charging seriously in California or some other areas other than China? That's my first question. The second question is, I have done some work that I analyze the case in California that you might be able to make a profit by transporting batteries from one side to the other using electric trucks to do special temporal arbitrage, using the price difference between different nodes, because there's a significant grid congestion between in local network because of the solar panels integration, while the distribution networks upgrade is very slow in the United States. So do you think this will also be a good opportunity for future research or commercialization? That you might have some trucks dispatched to some very demand-heavy spot in highway or for charging. So what do you think? Yeah, thank you.
Sure. Both are great questions. I won't have a complete answer to your questions, but I'll make a few comments. So the first question is about battery swapping versus charging. Love to hear your opinion as well, since you work on this, and also Peng Cheng's opinion as well. So many years ago, I was very enthusiastic on battery swapping, and that's why I suggested Quentin to look into that. At the time, several years ago, at the time, I think the only major attempt was a startup in Israel. This around 2012.
Better
probably.
place. Better place.
That's right. Better place. And they went bankrupt after $1 billion, close to $1 billion investment. And therefore, the challenges were non-trivial. I mean, there are lots of challenges. I think the technical challenges is the easiest. But then I feel that if it will be successful, it will probably be in China. Whether that experience can extend outside China remains to be seen. I think the challenges are mostly, I mean, there are many challenges. I feel the two most important challenges, they're not technical. One is just the ownership, right? So if you do battery swapping, the right way to think about that is really the battery is just a container that contains the energy that you buy, right? You rent a container basically, and then when the container runs out, you swap a new container with a full battery, for example. And therefore, the current ownership model where you own the car is not very compatible with that model. And that makes it very difficult because battery is probably the most expensive part at this point, still probably the most expensive part of the EV. And therefore, if you don't own that, that makes the ownership model and how everything works harder. It's not unsolvable, but it's much easier. For example, I guess in the Chinese case, the state grid. Many years ago, when Punchen works on that, the state grid, let's say at least the program, the pilot, the program at Hangzhou, they own everything. They own the cars, the drivers, the servers, the charging, and therefore there's no ownership problem, and therefore it makes a lot of sense. Now in the States, Tesla has on those highways, some highways, they allow people to do the swapping. At least on Highway 5 between San Francisco and LA, my understanding is that they discontinued that service. I don't know exactly why, but they discontinued the swapping service, which used to be available. And therefore, there must be some challenges. Again, I don't think it's technical. The second, perhaps, the challenge that needs to be overcome is standardization. So if you want to do it at scale, then the best thing to do is if all car manufacturers and the batteries, right, they standardize so that they can easily cross swap. At least the infrastructure doesn't need to be tailored for every manufacturer and so on. Again, those are non-technical problems, and I feel those are the problems that probably the biggest barrier. And this is also why I feel China's environment is best for solving these kind of problems. Outside, things are very distributed, so it's hard to coordinate. So the second question is the mobile batteries. Again, I think it's a great question, also a difficult question, because I think in general for clean tech, like compared with say IT, for example, the biggest challenge in clean tech is really the business model. I think the technology side is easier, and that's why this is a difficult question. Now, there are startups do some elements of what you said. I don't know how they perform, but whether they're successful probably has some implications on your question. So the startups that I know of, you use batteries to reduce demand charge. So there are startups and also big companies that actually do that. My understanding is that you could have a business case, but it's difficult. The profit is quite low. And therefore, at this point, if the cost of the battery continues to drop, if the the need, as you have more and more renewables and so uncertainties and so on, the need on the grid increases. Then the economics might change. The business case might become stronger. So far, my understanding is that it's possible to do a startup. Whether it is a very robust business model is not very clear to me. There's also a mobile battery, not exactly what you are thinking about, but they do mobile battery for charging. And therefore, what they do is that instead of using, so in PowerFlex, for example, what we do is that you build the local distribution grid within the garage to take the electricity from the grid and charge your EV. What they do is that they don't use they use batteries. They have batteries, they have chargers connected to the batteries that will charge the EVs. And they will ship the batteries to the garages periodically when the batteries on the chargers run out. And then that doesn't make sense, right? You don't use the grid to deliver your electricity, but you actually transport your electricity to the garage. So why would it make sense? Well, it turns out, if you look at the end-to-end providing charging system like PowerFlex does, the biggest challenge is actually designing for the garage, getting the permit, and then installing all the infrastructure for your garage. So that's initially can be 6 months to a year. And therefore, from the business perspective, that is actually a big bottleneck, even though technology is nothing. It sounds like trivial, right? We don't even think about that when we started, right? But it turns out that was a problem in the end-to-end EV charging service. And therefore, that model, which sounds ridiculous, actually solved that problem. No. And therefore, from the business perspective, what happened is that you have to understand end-to-end of whatever business that you're looking at, and then say end-to-end, there are multiple problems. You have to decide which problem you solve. Yep. The problem that PowerFlex solves is very different from the problem that this particular mobile EV charging solves. And therefore, that might is not exactly the scenario that you look at where you use mobile battery for to relieve network congestion, but it has some elements that's relevant. And therefore, I don't know the exact answer whether there is a business case for the scenario that you mentioned. But these are some of the thoughts.
Thank you, Stephen. I think they are very insightful. Both from the business model side and also from the potential batteries in the future low carbon system. Just a side story. So about I was also trying to look at the potential of battery swapping during my PhD. Oh, I did my PhD at Carnegie Mellon, where the other Guana is currently with. So
who was your advisor? Just curious.
So it's Shumar Carr and Jay Whitaker. So one in EC and the other in material science department. Both on batteries. So and then I went to MIT Energy Initiative for 2-year postdoc. And then so back to then, I was trying to look at the battery swapping, and then I saw the news of Better Place. Then I chose to don't waste time on that. And that's very that's right. I think so. The business really affects academia and also academics. Also maybe how to convert the academic works to business. As I really hope to learn more from you about this in the future. Yeah, thank you. I want to save time for other questions.
Yeah. Thanks, Guana. We do have a question from Hong Ling Ning in the chat, but it's a long question. I think 2 questions. Do you mind unmute yourself, like just discuss with Stephen? Okay, if not, I can help you.
Hello, can thank you. So I just repeat my questions in the I typed in the WeChat room. Also, Professor Low, many thanks for your profound presentation. As you know, so with the development of the power transportation network, it's like scheduling operation problem might be a very large scale problem, and it's time consuming to solve. For example, to solve the power flow in the power network, and in the meantime, scheduling problem of each EV in the transposition network. I might wonder, would you suggest any kind of more convenient modeling method comparing with the traditional ones? And also my second question is, from the view of charging station or chargers, it may be difficult to collect the data of the users or EVs due to the privacy issue. So from your experience, I see you have established the real chargers in your lab. So can we still obtain some further characteristics of EVs through the charger information by some method, like for example, the real-time SOC of EVs, just like the transformation process you have introduced in the distribution network. Also, I just typed my third question. My third question is, one of the advantage for the large-scale EVs to the power network is they can provide resilience or emergency service. This also kind of one auxiliary service to the power grid. So there are still some research focus on this, but currently, as we know, there are already like the power supply vehicles of the grid companies. So Professor, what do you think of the research potential in this field, like the EV to provide resilience to the power grid? Thank you.
Sure. I didn't quite catch the second question. What exactly is the question? But let me just comment on the first and the third. So indeed, the first question, right? I guess if I understand the question is that the computation from, if you want to look at EV charging and the grid impacts and all of that, can be the model at the end you have to solve can be too complicated, especially if your application require real-time decision. So what can be done? So I think certainly the details depends on the application, but I think that in general, you have to look at, for your application, what are the uncertainties, the noise, typically we call them noise in the model, and what is the required accuracy for your decision. So for example, let's say in our case, EV charging case, we actually don't fully take into account of the power flow in the network, in the distribution network within the garage. What we do take into account is the three-phase, the effect of the three-phase power flow on the capacity limits. So these are sort of safety constraints, right? So those will be, we want to make sure that the three-phase power flows will not exceed the, say, the breakers capacities or the line ratings and so on. But we don't take into account full account of the power flow behavior of the distribution network, for example. So that is an example of you ignore certain parts of your model, right? You have a very coarse model. Then the question is that would that be sufficient for your application? And I think this will be the most important approach to simplifying your model. One justification, I just heard a talk before this talk, that shows in the LTI linear-based control kind of framework that shows rigorously the following insight, where suppose you have a certain noise that has a certain, let's say, worst case magnitude, and then you don't know the system, and you try to identify the system so that you can control. Well, it turns out it doesn't help you to identify to an accuracy that's higher than the error produced by your noise. And therefore, you don't need to do that much of a computation because the more computation is not going to help you. And therefore, I think this kind of thinking, this kind of approach, what kind of accuracy you need, and it is possible, I think is an important consideration in how you simplify your model and therefore simplify your computation. So your third question on this V2G. So indeed, recently, I think Ford, for example. So first of all, I think on the hardware, it's not hard. It's certainly possible to do. It's certainly possible to do vehicle to grid. The question is whether it is worthwhile to do it, right? And right now, most of the car manufacturers do not allow people to do that. By default, you just cannot do it with your car. If you play with the car to do it, you may void your warranties, for example. But Ford now, I think either they're piloting or they already allow you to order a truck that will have the V2G capability. And therefore, I think it will happen, even though it has not really happened yet. But I think it will happen because the value, as you alluded to in your question, is tremendous. An example is that in 2020, August 2020, there were rolling blackouts in California. So that's very destructive at the state level. There were 2 days where there were rolling blackouts. To save, to reduce the demand by 2 gigawatts, is 1 gigawatt for 2 hours, right? Now, if you assume future EVs have at least 300 miles of range, and if you assume people are willing to use just 20% of that capacity in times of emergency to help the grid, then you only would have taken 100,000 EVs to have avoided the blackouts in August 2020 in California. So that seems like a tremendous value, right? Even if you just compensate for the EVs during that emergency, even say $100 per for that event, is only a couple million, a million or so dollars to have avoided the whole blackout for the entire state. And therefore, I think this is just one example of emergency use. There are many other examples you can think of where I think the value for V2G is quite compelling. Whether there are, so what are the technical challenges that need to be overcome or interesting technical research problems, and then whether one can design the right policies and market incentives to incentivize people to do it. Well, I think so on the technical side, there are certainly, I guess, pilotronics things one can do. I assume that's already possible, but you can always improve that. At the system level, right, at the grid level, you have EVs everywhere, let's say some residential parts on the workplaces and so on. Then you can, I guess, formulate a problem. What is the best way to utilize the available batteries that are temporally and spatially distributed and varying as well, right? Related to the earlier question. Then what is the right mix of V2G services you want from this set of EVs, right? That seems like a really interesting problem because the EVs, they may have different state of charge, they may be driving to different places, they may have different transportation needs, and then you have this, and therefore those dynamics and those needs are both temporal and spatial. And then you have a grid whose needs is also temporal and spatial. So how do you match the two, right? I think it's a very interesting technical problem to formulate and solve. And then once you have these sort of technical problems, can you design incentive structures to incentivize the right behavior, right? If you assume there's no centralized command that controls every EV on the grid to say you produce this much at this time at these locations and so on, but rather you have some kind of incentive and allow people to make their own decision in a distributed manner. Can you design incentive structures so that their individually optimal decisions turns out to be socially optimal? So those, I think, are all interesting problems to formulate.
Okay, thanks for your explanation, Professor. Thanks so much. Yeah, just as you mentioned about the first problem, it's a very large scale problem, just to decide where to locate the EVs and how many powers, how much power they should charge or discharge, and also need to consider the power flow issue or the cost issue. It's a kind of very large problem. Also for the second problem, because for the chargers, we might only know the charging time, charging duration, and the charging power or charging energy of each EVs. Right? We can collect this kind of data, but what we don't know is like the real-time SOC of each EV. We cannot see from the chargers or EV stations. So, but this is also very important. I think it's important information for the EVs, for the transportation network or the chargers. So my question is how can we still obtain this data from what we have obtained in the chargers? So my question is this. So I might. Yeah.
I see. I think number one, I think the state of charge is extremely important, and it's not very clear why when they design the standards they do not communicate this piece of information to the charger. It's certainly available in the car, but they don't communicate to the charger, right?
Yes.
And there were some of the challenges that we dealt with at PowerFlex actually has to do with this, the fact that we don't know how state of charge. However, and therefore, one can design clever algorithms to try to deal with this issue. Another approach is that indeed people in the standardization community, they are standardizing new charging protocols that will provide this state of charge to the charger. And therefore, maybe in a few years, this problem will disappear.
Okay. I know. Thanks.
So one of the learning problems, for example, that I mentioned in ACN data has really to do with the fact that we don't know state of charge. If we're new, then the learning problem becomes much easier.
Yes. Okay. Thanks so much, Professor.
Sure.
Hello.
Yes, hi, Feng, how are you?
Yeah, hello. Thanks, Stephen, for a very inspiring talk. I just have two questions. One is very detailed, and the other is quite general. First question is about the first part of your work, your talk. The semantics identification or similar learning techniques.
The audio is very difficult for me to hear. I don't know whether other people hear that.
I think Professor Liu Feng, your mic is not so good.
Hello?
Yeah. The volume is high, but it's hard for me to. Yeah, maybe the noise.
I can use that. Better?
You can try again.
I just have two questions. One is detail, and another is general. The first question is about the first part of your talk. And I noticed one of the key assumptions is the degree at least 3, right? Just
one of the key assumptions is what?
It's a hidden node has a degree at least 3.
Okay, degree 3, yep.
Degree 3. And but in distributed network, the degree, if the degree is 1, it should be either any node or
sorry, I couldn't hear.
Okay. I just to otherwise.
You can type it in the chat, Liu Laoshi.
I just type it. Okay.
I think it's sort of related to my question, Stephen. So I'm wondering what happens if the hidden node doesn't have a degree of 3, and also so what's the intuition of that decomposition? Because you subtract from the regional matrix, the diagonal of the column sum, right? How does that lead to this decomposition?
I see. Yeah. Sure. So the first question, the degree 3. So it's not a critical assumption. What it means that, let's say if you have a hidden node with only degree 2, right? So it's a hidden node connected to two other nodes. Those could be hidden or measure nodes. Then you will not be able to identify this hidden node, degree 2 hidden node. All you see will be the two other nodes that's connected to this degree 2 nodes. That's all it is. You won't be able to resolve that. The reason, algebraic reason, is that in step 2, where you figure out the line parameters between a boundary measure node and boundary hidden node, in that step, you need 3 equations essentially to solve for that parameter. That's where the degree 3 comes in. Yeah. Otherwise, you just don't have enough equation to solve it. The second question.
The linear recursion won't work, right? If you have a hidden node of degree 2.
So
linear recursion.
Yeah. So I think what will happen in the recursion, the whole thing is that your original network what you will identify will be a network where all degree 2 networks will be sort of cone reduced. You won't see that. You just see the nodes that this hidden degree 2 nodes is connected, assuming those two nodes have degree 3. That's what you get, I think. My guess is that I have to confirm, but my guess is that the recursion will work, but you end up with not the original network. But the only thing that's missing are those unresolved nodes.
I see.
So your second question,
the intuition of that decomposition.
Yeah. Maybe the best intuition is on the graph side. So what happened, if you remember, you may not one of the slides where you have an example, several nodes, and then there's one node in the middle that is hidden. Mm-hmm. Then if you look at sort of cone reduced graph, which intuitively you're probably familiar with, right? If you do the cone reduction stuff, all you get is that the 3 nodes that are connected to the hidden node becomes fully connected. Yep. And therefore, in the cone reduced network, you will always have a structure where you have these cliques, which will contain some hidden nodes underlying the cliques. And then you have trees, because the assumption is the original network is a tree. So that's where the tree assumption is important as well. And therefore, the cone reduced graph is always going to be a whole bunch of cliques and then trees. For those regions where you have only trees, there are no hidden nodes. Mm-hmm. Whenever there's a hidden node, you always get a clique. That's what the decomposition is.
I see. Okay, I see Professor Fong's question here. Did you see it?
Yeah, I'm reading that. Yes, that's right. So typically, the end nodes presumably are measure nodes where you will have, let's say, loads or generation, and therefore, yes. Otherwise, sure, then you won't be able to. I guess your question is that if that's the case, if you have degree 1 nodes that are hidden, can you start the recursion? I think so. As long as, so you certainly need certain part of the network to have degree 3, for hidden nodes to have degree 3. Otherwise, yeah, you won't be able to solve for this white hat in step 2. So for the step 2, you need some degree 3 hidden nodes. But I think with that, I think the rest should be fine. I have to confirm. Oh, that's a degree 3, right? Okay. Do you have a second question?
Yeah, there's a second question.
Okay.
Breaking. So
which type of work is more important? What? Oh, practical deployment versus the theory? Oh, okay, sure. So this is a high-level philosophical discussion. I can send you an article that I wrote recently about my experience with the first startup, which touch upon this. So the basic message, I think both are important. I think that there's a spectrum of good research, from very theoretical, abstract, that may not have any application, perhaps, in the foreseeable future, to something that is very practical, that's directly deployable, and anything in between. I think the whole spectrum is important. Where one sits in that spectrum depends on one's interests and background and everything, I think. So one comment related to that is that, so I'm interested in the intersection. That is, right. So some good research that will have practical use, right? But I have a lot of admiration for people working in their complements. I think they're doing great work, right, and useful work. The question is, why can't we just focus on research that is at the intersection? Why don't we just focus on good research that has more direct applications? I think we cannot do that for two reasons. One is that it's very difficult to predict what will become practically important. And there are many examples where things become extremely important after decades or even after centuries. It's even difficult to predict what can be important a few years down the line. So in that article, I have an example where when I was a student, I was at Berkeley. By the way, is already more 5 minutes, 6 minutes past. So I don't know. Should I stop or?
I think it's fine. As long as you are flexible with the time.
Okay, sure. I am.
Continue.
So whoever needs to leave, please feel free. Great to see old friends, so we can talk. So one example is that back in early 90s, 1991. So I was Berkeley. I was a PhD student. So so the student committee meeting those faculty candidates, and one of the candidates in meeting with the student committee declared that information theory is dead. But only a few years down the line, it becomes so important. I mean, information theory came back in a big way because of the wireless revolution that happened in the 90s. And this is just one example among many where it can be difficult to predict what is useful only a few years down the line, right? And then there are many examples that takes long. The second reason I don't think it's possible or desirable to focus only on good theory research that has practical value, because I think that is the research enterprise is like a tree. You need a healthy root system and the trunks and the branches and the leaves in order to have really good, say, flowers and fruits. You cannot have just flowers and fruits without those foundations. And therefore, I feel theory research is probably one of the best ways, not the only way, but it's probably one of the best ways to really nurture the kind of intellectual fearlessness, the kind of the habit of really cutting through details and get to the core of the problem, really look at the fundamentals in the most simplest way. And I think all these capabilities, I think can be one of the best ways to nurture that is good theory research. And therefore, yet these characters are important in dealing with many of the complex practical problems. And that's why I feel it's not possible or desirable to focus, to say, okay, I only want to invest in research, good research that has practical value. I think we just have no choice, that we have to encourage a whole spectrum of research. As long as it's good research, doesn't matter where it sits on the spectrum.
You're muted.
Thanks, David. Yes, pass through to our leader.
We have another question in the chat. Could you tell a little bit more about the business models of ACN at Caltech?
At Caltech, there's not much of a business case. I mean, it's a commercial operation in the sense that people pay to charge. On the other hand, it's not that Caltech wants to make a profit out of this EV charging. They just want to recover the cost. Recover the cost, which mainly is electricity, because the infrastructure is sort of a sunk cost. And that infrastructure, we apply for research grants and stuff to pay for anyway. And therefore, there's not much of a business component at Caltech. So if your question is the business case or business model for PowerFlex, so that's a long discussion. I guess the fact that the company seems to be doing well suggests that it does have a business case. On the other hand, so I was involved at the beginning, so I'm no longer involved. I don't know their day-to-day operations and so on. So from my experience in the beginning, it is difficult. It's challenging. And I don't think that is unique to EV charging or PowerFlex. I think it is quite general for clean tech. I think the clean tech very often, the business model, I mean, there are exceptions, of course, but in general, the business model is more challenging than, say, IT startups or financial fintech startups. Yeah, I mean, there's a long discussion on why that is the case and if anything can be done about that and so on. But yeah.
Thank you, Professor Low. That question was from me, and I wanted to know if you have considered by controlled charging on the customers' vehicles, whether that will change their behavior. So I wonder if you use price as some leverage so that they would be more interested in like saying we can charge the car for a longer time instead of a shorter period.
Right. Yeah. So that's a great question. So in theory, one can formulate models and so on to do exactly what you said, and then depending on how you design your incentive structure, you may have different resulting behaviors and so on. Right? So on the theory side, there are many things that one can explore, even have some game theory behaviors between the drivers and the side hosts and all of that.
Right.
Now in practice, though, I don't think PowerFlex. So certainly during my time, we did not explore that at all. I'm not sure PowerFlex today or any company today explores explicitly that. Now certainly how the payment scheme that you use, so some use, let's say, just based on time. It's like a space that you are charging, for example. Some based on energy, some based on some combination. And as you suggested, you can base your charging partly to encourage laxity, the flexibilities, and so on. So I don't know any charging company, including PowerFlex, tries to do that to encourage flexibility. But it's certainly something that seems to make sense. Yeah.
Yeah, we in our company, we are actually helping the companies providing charging services who build charging stations to manage the charging load. But also, I think naturally, your team probably also considered to aggregate the charging load to, let's say, participate in demand response or directly in the wholesale market. And then, yeah, if you do that, then you probably would need to consider some incentives to the customers.
Yeah, that's a great point. That's a great point. So to me, something intellectually, I think that's a great thing to do. And with proliferation of EVs, right? These are large and extremely flexible loads. That seems to be a really great thing to do. And especially there are startups just try to do that using batteries. And then you will say, well, if anyone using battery can have a business case, obviously, if you do control, you manage your enough EVs, you will have a much stronger business case. Unfortunately, and therefore I agree completely with you. I think that would be something that would be really nice to try in practice to see how to build a business on that and everything. And then all you said makes sense. Trying to design incentive programs that actually, so that you can pretty finely control or predict the behavior, the resulting behavior becomes very important. The fact that no companies or PowerFlex has done that is because they have not gone to the step of trying to use this to provide great services in the market.
Okay.
Why not? Why not? So
is it a volume issue?
Sorry?
The volume, the size of the total charging load is not big enough?
That's one big question. So from our personal experience, the reason we did not do that, even though we had in mind of doing that at some point, was that one is that problem that you mentioned, that there was just not enough volume when we first started. Secondly, in California, CalISO, for example, we had a consultant early on that told us you will probably need at least half a year of at least one full-time person and at least maybe $500,000 to set things up, just to set things up. And at the early stage, we just did not have the resources to do it.
I see. Okay. So it's a business barrier. So the business process. Yeah. Okay. Got it. Because I've checked, like in California, the three big IOUs, they all have demand response programs. I wonder probably some of the public EV charging facilities would consider participate directly or through some aggregator to the demand response program. And then the EV, how to model the EV load, the aggregated EV load, would be a very interesting problem. We are facing this problem right now.
I see. There's some work, really interesting research work to try to look at the aggregate flexibility. Exactly what you said. If you have a whole bunch of distributed energy resources, each has its own requirements and dynamics, and it needs to do whatever it does, right? The charging EVs meaning that you have to provide certain energy within a certain time. So in general, you have a bunch of distributed energy resources. They have their own dynamics and requirements. And what is the aggregate flexibility that can be provided? It's really interesting research question. There's some work, but it's still, I think, a somewhat open.
Yeah, so there still needs some practical work from our point of view. Right. Well, thank you very much for sharing your thoughts, Professor Low. Appreciate it.
Sure. Thanks for the good questions. All the different questions, there's some business component that's tough.
So I think we go beyond too much time. Maybe it's time for close the seminar officially, but we can continue the discussion, like Stephen, if you have time. But maybe we can stop recording.